Good afternoon, everybody. Good afternoon. Before I introduce this afternoon's plenary speaker, just a couple of bits of housekeeping, a couple of reminders. We have the poster session starting at 6 o'clock later today, and then also starting at 6:30 is the movie that Stacey mentioned this morning, followed by a Q&A panel session. There is a bit of overlap between those, but if you'd like to go to both, I'll leave that to your own scheduling. Now, to this afternoon's plenary. I'm delighted to introduce Professor Julia Baum. Julia holds the Faculty of Science President's Chair at the University of Victoria in British Columbia in Canada, where she is a Professor of Ocean Ecology and Global Change in the Department of Biology. Now, Julia's research group works to advance understanding of the ecological impacts of climate change in the ocean, especially tropical coral reefs and kelp forests, and to inform and catalyze climate solutions. Julia completed her PhD at Dalhousie University, also in Canada, and was then awarded research fellowships at Scripps Institute of Oceanography and the University of California, Santa Barbara, before joining the University of Victoria in 2011. Julia has a number of significant achievements, and these include being named as an Alfred P. Sloan Research Fellow in Ocean Sciences in 2011, a Pew Fellow in Marine Conservation in 2017, and an NSERC EWR Stacey Memorial Fellow in 2018. In addition to her various accolades, Julia is a strong advocate for equity, diversity, and inclusivity in academia, and devotes considerable effort towards communicating science and the need for climate solutions to policymakers and the public. With that, please give Julia a very warm welcome to the stage.
Thanks so much, Simon. Thank you, Simon. It's a privilege to speak with you all this afternoon. This story starts, like most of our stories probably do, with a biologist falling in love with a coral reef. And for me, that was this reef on the remote end of Christmas Island in the central equatorial Pacific Ocean. Accessible only via an arduous, somewhat sketchy shore dive, which is how I first encountered it about 20 years ago when I was a postdoc at Scripps Institution of Oceanography. Few people in this world had seen this coral reef, and I was enchanted with it. I vowed to continue studying it and establish a long-term monitoring program at it, even though I had no idea how I would go about doing so at the time, not having a permanent job, not having any real research funding, and there not being a field station on the atoll from which to work. But I was convinced that this reef had a lot to teach us about how coral reef ecosystems function when they're unencumbered by human disturbances. And I thought that I would study how coral reef food webs are structured in the absence of such disturbances, and then how they fall apart with overfishing, which is what I was actually trained to do. But the world, as I'll share with you this afternoon, had other plans. This reef has now become one of the poster childs for climate change because of what it endured. And my message for all of us this afternoon, echoing what Ove told us last night, is that we're not going to save this or any other reef if all we do is continue to study them. Alongside our coral reef studies, I believe that we must each also start investing our time, energy, and efforts at the root cause of the coral reef crisis, the greenhouse gas emissions that are causing climate change. And we must work together, collectively, to advance real solutions to this crisis. What I'll share with you over the next half hour is the story of how I came to this viewpoint, the key scientific discoveries that we made about coral resilience along the way, and the path that I'm now on and attempting to forge in my own life, which I hope will help to provide some food for thought for you about changes that you might think about making in your life, or at least spark some meaningful or controversial dialogue amongst us this week. To begin, I want to center who I am. I'm a second-generation settler in Canada who has the immense good fortune to live and work on the Lekwungen, Songhees, Quisepsum, and Wasanich peoples' territory on the west coast of British Columbia on Vancouver Island. And my positionality as a Canadian studying tropical coral reefs far outside of my home country's territory. Kobasin Rabwa to the people of Kiribati, where I have worked for the past 2 decades, for sharing the Te Aba with me and with my team. It is such an honor to work with you and to be able to study your coral reefs. And as all of you know, science is a team sport. And I would not be here today if not for my mentors, colleagues, collaborators, friends, students, and postdocs, a number of whom deserve special mention now. First, Jeremy Jackson, who I had the great good fortune to land with at Scripps. Bonded by our mutual love of historical ecology and long, long dinner parties, who set me on the path to Christmas Island, encouraged me to continue to dream and think big, and to observe the reef carefully. To Ruth Gates, who welcomed me into her coral symbiosis fold, even though I had no business being there without the training, but who became very quickly a dear and now missed friend, mentor, and collaborator. To Kim Cobb, a force of nature who taught me about El Nino and who banded together with me to study the 2015-2016 El Nino on Christmas. And to Andrew Baker and Ross Cunning, who continue to guide me and my students in our coral symbiosis studies and do so with such exceptional care and generosity. Danielle Clark is my first coral symbiosis student, and Christina Tijan joined the lab shortly after Danielle did, which is now somehow already over a decade ago. And Alex Van Nijneten and Mika de Bruin have joined the lab more recently as postdoc and PhD student, and Christina and Alex and Mika are all here this week right up front, and I know they would love to speak with you all. So the reef that I first showed you, Christmas, and the whole atoll more broadly, which is what you're seeing from the satellite image here, are the stars of this afternoon's show. And to orient you, Christmas is found in the central equatorial Pacific, as I said, and it's due south of the Hawaiian chain of islands, which is the yellow dots that you see there, so due south of Honolulu, all the way down almost to the equator. It is home, as I said, to the ICRS people, and it is the world's largest atoll by landmass, with a perimeter of about 150 kilometers. And it's one of 32 low-lying atolls and islands that make up the Republic of Kiribati. And my team and I feel so fortunate to get to work in this beautiful island and in this country. What drew me to Christmas initially was its exceptionally strong gradient of local anthropogenic disturbance across the reefs on the atoll, with reefs nearest the village looking like the one that you see on the left here, and reefs at the farthest other end of the atoll looking like the very near pristine reef that you see on the right. Through census data and interviews, we quantified the human disturbances at each of our 40 shallow 4 reef monitoring sites, and these disturbances are primarily from dredging, sewage, pollution, overfishing, kind of the usual suspects. And we categorized each site as being exposed to very low, low, medium, high, or very high disturbance. And this atoll scale, or ecosystem scale, natural experiment really has formed the foundation of every study that we've done on Christmas Island. But of course, climate change is superimposed on all of the anthropogenic disturbances that reefs around the world face. And the catalyst for this story is one climate change amplified marine heat wave in particular that you see here in the red band, the 2015-2016 El Nino. Marine heat waves are now arguably the greatest threat to the world's coral reefs, and El Niños, supercharged by climate change, are the primary source of marine heat waves, and so correspondingly of global climate coral bleaching events. Now, we didn't know all of this at the time that we started awaiting this El Nino back in 2014, but what we did know was that the El Nino was predicted to be the biggest such event on record, and it was predicted to center right in the central equatorial Pacific inside that black circle, which is where Christmas Island is, and where at the time I had 6 years of baseline data in my hot little hands. We knew this event would give us the opportunity to try to understand why some corals are resilient to heat stress, while others bleach, even when they're sitting side by side, ones that are just fine, when they're in the same water and the same environmental conditions. And scientifically, I'm not going to lie, this was a dream come true. Because I am fundamentally an ecologist who is hell-bent on understanding the sources of ecosystem resilience. And studying resilience requires subjecting whole ecosystems to a large stress to try to understand why they might be able to resist that stress, how the stress reshapes them, or how they can recover from it. And it is enormously difficult to plan such events, of course. And so we had this amazing opportunity before us. So it was a hugely exciting and also very stressful time for us in the lab. Now, what we could not have known was, or foreseen, was the extent of damage this El Niño would do to the world's coral reefs, because this is what became the third global coral bleaching event. And we could not have foreseen how hard it would hit Christmas. Christmas is right in the middle of that red blob. It landed on Christmas in about May of 2015, and it never let go. Along with nearby Jarvis Island, Christmas was the hardest hit place on the planet, enduring almost a year of unrelenting heat stress. Scientists had predicted this amount of heat would not occur on any reef until mid-century. But Christmas broke all of the records. And when you now see NOAA's Coral Reef Watch designations of Alert 3, 4, 5, this El Niño is why. When we were first able to get out onto the reef in July of 2015, about 2 months into the event, this is what we saw. Patchy bleaching, variable across taxa, and overall there was about 30% bleaching at that time. Fast forward to December of that year, and the reef had changed radically. Much of the reef was dead and already overgrown by turf algae, and much of the rest was ghostly white, being bleached. By the time we returned at the end of March 2016, 10 months into the heat stress, all of Christmas's large plating acroporas were dead. In fact, most of the reef was dead, including the distinctive acropora at my favorite site. The devastation and the accompanying ecological grief were harrowing and hard to overstate. Sure, amidst the carnage, some corals survived and even recovered by the following year, and some corals appeared to come through the event unscathed somehow and were thriving by the following year. But by and large, Christmas's reefs, now the bellwether for coral reefs under climate change, were devastated. And we documented at sites around the atoll a loss of almost 90% of the hard coral cover. So there's that mortality that Greg was talking about this morning. Now, more broadly, we also documented changes in soft corals, which are often overlooked in bleaching studies, and we found the complete loss of soft corals at all of our monitoring sites. We'd been working with John Burns, one of the pioneers of structure from motion photogrammetry, and I believe John is in the audience somewhere. And together with John, we had quantified habitat complexity at our sites around the atoll before the event and then after it. And of course, habitat complexity is one of the key drivers of the immense biological diversity of coral reefs. But not surprisingly, given the extent of coral mortality, habitat complexity declined a lot overall, which is what you're seeing in the blue boxes, and then across each of the disturbance levels. We had also counted tens of thousands of fishes of 245 different species around the island for many, many years prior to the event. And through repeat sampling, we're able to show that early on in the El Niño in July 2015, the reef fish numbers at our sites had dropped by about half, which was alarming. But within about a year, almost all of them, with the exception of the obligate corallivores, had bounced back. And so what we surmise is that the reef fishes had simply gone to deeper waters to avoid the uncomfortably warm water. Now, returning to the hard corals, we documented, as I said, almost 90% loss, 89 to be precise. And what you'll also notice, though, in the dark purple box on the left, is that there is quite a lot of variability in the percent of hard coral cover prior to the event. And that's because of this disturbance gradient, which you can see here for the very low, medium, and very high sites. The heat wave also played out in differential losses across this disturbance gradient, with sites exposed to very low disturbance experiencing much greater losses than those that had already been diminished due to other local disturbances. But this is not simply a matter of having more to lose, but rather to differences in coral community composition prior to the heat wave. So low disturbance sites tended to be dominated by corals. We've got them color-coded here in sort of blue colors. Those are corals that have competitive life history strategies, like Montiperas and Acropora. And these species experienced much greater losses compared to their stress-tolerant counterparts, such as Porites lobata. This highly variable interspecific mortality leads to what is becoming one of the dominant signatures or outcomes of heat waves, which is these winners and losers. Here, all of the competitive corals in blue are underneath the zero line, so they were losers, and almost all of the stress-tolerant corals were winners. The biggest winner, the one on the far left, was Platygyra, which really increased its proportion on the reef the most. But one of the other big winners, and the biggest from a different perspective, is that third one in the dark red, Porites lobata. So Porites started the heat wave already as the most common coral species, and it increased its real estate on the reef, doubled it during the heat wave, and so came out of it, ending the event being over half of the atoll's remaining coral cover. So this very prolonged heat wave caused these massive losses of hard and soft coral and substantial turnover in the community that remained. But why? To understand the mechanisms of coral resilience, why certain corals were able to survive this duration of thermal stress or bounce back from it quite quickly, we needed to look inside individual corals. And this is where my training as a fisheries scientist and a great lover of time series analysis actually served me well. Because while it's much more common now to tag and track corals, it was not exactly the norm back when we started in 2014. But we knew that following individual corals, like patients in a long-term clinical study, and assessing their health, whether they were alive, whether they were bleached, whether they were dead, and critically their symbiotic partners, would all be critical to documenting and really understanding mechanisms of resilience. So we set out to tag as many individual corals as we could at sites around the atoll. Focusing on the 7 species outlined here, 5 stress-tolerant and 2 competitive species, and managing to tag well over 1,000 of their colonies before the end of the heat wave. I'm going to tell you the story of 3 of these species now, and the mechanisms of resilience that they revealed to us throughout this heat wave. So this first story is about Platygyra rucuensis, the brain coral, and this is work led by my then PhD student, Danielle Klaar. Now, when we first tagged these corals back in 2014, which is well before the heat stress, they were healthy, as one would expect, and they continued to be healthy. And then at our first time point in the El Nino, that July 2015 time point, a lot of the brain corals were bleached. Now, of course, what we expected is that the corals that survived this event would be the ones that could kind of wait out the heat stress and then take up symbionts again after the heat stress had abated. This is, of course, the dominant paradigm of how coral bleaching works. Instead, what we found were corals that took up symbionts again and recovered while they were still subjected to heat stress. Now, to say that this surprised us would be a grand understatement, because frankly, at that point, I was shocked that any coral was still alive. All of the corals on the island had been sitting in a hot water bath for 10 months at this point. But these brain corals managed to do this. But we found that they were only able to do this if they were located at sites that were not exposed to very high levels of human disturbance, suggesting that local protection can confer resilience to corals. Okay, but how did they pull this off? Well, I want to channel Ruth just for one moment, but I'm not going to torture any of you by trying to do an English accent. But just think about Ruth saying this, and I know a lot of you will be able to hear this in your heads. It's the symbionts, baby. The symbiotic partners that brain corals had going into the heat wave depended on their exposure to local human disturbance. So brain corals at the very high sites, that's kind of the dark rust color, they all started the heat wave already partnered with Duristinium. Brain corals located at any other level of disturbance went into the heat wave partnered with Cladocopium. And perhaps counterintuitively, but I actually think not, it was those corals that were partnered with Ds that almost all succumbed to the heat, while those that started with Cs bleached and then took up Duristinium partners while still subjective to heat stress. Now, this work carried forward by my recently completed PhD student, Daisy Bozzoni, has shown that the Duristinium have persisted in these Platygyra survivors. And they've done so up until 2019. And then we had quite a bit of a hiatus because we couldn't get to Kiribati for 3 years during COVID. But when we were finally able to return, what we found is that Platygyra still is mostly partnered with Duristinium, and if anything, it seems more entrenched now than ever. And so this is a mechanism of resilience by which this coral was able to get through this really prolonged heat wave, but the functional consequences of what it cost it are still really unknown, and there may be trade-offs. One of the consequences that we do know is that it has come at the cost of symbiont diversity in this species. So the Cladocopium species hosted by Platygyra prior to the heat wave are shown here by their ITS2 profiles. So what you're seeing here is each row is one of our tagged coral colonies, and they span from the very low through to the very high sites. All of the types of Cladocopium that Platygyra was partnered with prior to the heat wave, those are shown in the different shades of purples and greens, are no longer partnered with any Platygyra that we found on the island. So we have this disruption of coral symbioses and the loss, as far as we know, of some of these species. Paredes lobata, the main character of our second story, doesn't have the same symbiotic flexibility that Platygyra does. So here we decided to investigate if the resilience might lie within the coral host itself, specifically in genetic differences amongst these morphologically indistinguishable colonies. Directional selection imposed by marine heat waves can, in theory, drive cryptic losses of genetic diversity within taxa, but this phenomenon has rarely been demonstrated in marine species due to the lack of longitudinal genetic data. And this was work led by my postdoc, Sam Starko, and a great collaboration with Sarah Davies, who I think is here, hopefully somewhere, and her lab, and Andrew Baker and Ross Cunning. So we used 2B rad sequencing to characterize the genetics of these corals. And what we found was that there are, in fact, 3 distinct genomic lineages of Paredes lobata on Christmas, which we have named PKIR, P for Paredes, KIR for Christmas. So PKIR 1, 2, and 3. And these lineages had substantially different survivorship throughout the heat wave, ranging from a low of only 15% survivorship all the way up to 64%. And this was because whereas PKIR, which is the pink line that you see going across the top, had pretty high mortality regardless of where it was on the island, mortality of the other 2 lineages was pretty low at low disturbance levels and only really rose when it was at higher disturbance levels. So there were also differences in the symbionts, in the symbiotic partnerships of these lineages that I don't have time to go into, but if you're interested, I'd encourage you to take a look at the paper. Overall, however, we think that the evidence suggests that it was the genetic diversity of Paredes at this location that facilitated its resilience to this heat wave. Finally, Passalopora grandis, the sole competitive coral species in these vignettes. And this species was quite common. It's within all the green circles prior to the reef, at sites around the reef. But unlike Platygyra and Porites, it suffered really high mortality. Work led by my postdoc, Alex Van Nijneten and Ross Cunning, has shown, however, that Passalopora, because of its really high population growth rates, has mostly rebounded at this point, largely recovered its coral cover by 2023. And while its pre-heat wave symbiont lineage, which we're calling Cladocopium latticeorum lineage 1, declined and was replaced by Juristinium during the heat wave, and that persisted for a little while, what we found when we got back out there in 2023 was that most of the corals by 2023 were now partnered with that original pre-heat wave symbiont, so unlike Platygyra. So we might surmise that is both Passalopera's fast population growth rates as well as the reestablishment of pre-heat wave symbionts that has facilitated its resilience to this event. Okay, so I've told you 3 different mechanisms of resilience that corals can have to even very prolonged heat waves like this one. So corals do have a diversity of strategies that they can bring to bear on climate change. All is not lost. And yet, the prognosis is not great, and we had this 3-year waiting period where we were kind of waiting and nail-biting and wondering what was going on, knowing at the same time, while we were wondering what was happening to Christmas's reefs, that the ocean was getting hotter and hotter and hotter, and yes, some scientists like me were freaking out. So we didn't have really high hopes of what we were going to see when we got back out to Christmas in 2023. But coral reefs never cease to amaze and surprise. And what we have found is that even at unprecedented levels of ocean warming, coral recovery is possible. What you're seeing here is just one of our sites on the left before the 2015-2016 El Nino, immediately after and in 2023. Across the atoll, we find that coral cover on Christmas has recovered almost by half to 47% of its pre-El Nino levels. So that on average now, there's about 18% coral cover at sites, which I know probably sounds good to a lot of you, but for us is still shockingly poor. And of course, there's a lot of variation across sites, which you're seeing in the different lines spread out on the graph on the right. And this variation across sites is also visible here in this plot, where each column or box represents one of our long-term monitoring sites. And the widths of the boxes are scaled to the percent coral cover that that site had prior to the El Nino. So you can see the kind of rusty brown sites in the middle where it says northwest. Those are the sites that are exposed to very high disturbance, and so they have a very small share of the overall coral real estate. And then moving out to the sites under very low disturbance, the coral cover gets wider and wider. Now, above the 0 line in beige, you see the amount of coral that survived the heat wave, and in purple is the amount of coral that had recovered by 2023. So that seems pretty good for some of the sites, but the height of the gray bars below the 0 line shows how much recovery is still waiting to happen. So yes, we see a lot better recovery than we had feared or anticipated. There's a lot of variability across the sites. A lot of the very low sites are not doing as well as one might hope, and there's still a really long way to go. But this is a reef that looks like it is recovering. This is one of Christmas's sites, one of our sites in 2023. And I can also tell you, since you're probably all wondering, no, it did not incur really any impacts from the 4th coral bleaching event in 2023-2024. So on the left, one of our sites in 2023, where we were out there just as the heat was starting, and a year later, after the heat stress had abated, and really we can detect no mortality from this event. So not every event, even when it's called a global coral bleaching event, is going to cause mass mortality at every site. Okay, but Christmas isn't out of the woods yet. We also know, and we saw another version of this last night in Ove's talk, that the oceans are now warmer than they have ever been. So this month, July, oceans are now the warmest that they have ever been in any July. And we know that the El Nino, the super El Nino that's been predicted for many months, has now started, and it started months before it should have, because El Ninos really are meant to get underway closer to December, hence the name. But this El Nino is already underway, and Christmas, we know, is now already on bleaching alert 5. So it seems highly unlikely that this reef's recovery is going to continue, and we'll know in a few weeks when my team gets back out there. I don't have the hubris to say that we should give up, but I, for one, can't simply keep going like this, documenting the demise of nature. And that is what we're all going to be doing if things don't change. Because there's no turning this around for corals until we put the brakes on this runaway warming. We must, as Ove urged us to last night, stop burning fossil fuels and aggressively mitigate climate change. Anything else, I'm afraid to say, is a Band-Aid at best for coral reefs, and we need to face this. This is one of the figures that keeps me up at night. Wasn't sure if you'd be booing at this point. This is one of the figures that keeps me up at night, but this is a figure that gets me up in the morning and spurs me on to action. Because we have the capacity to solve this problem if we choose to do so, as this figure from the latest IPCC assessment report shows us, with a suite of different future emission scenarios. I think about this figure all of the time, and I think about the inequity of climate change as someone from a country with one of the highest per capita emissions rates in the world, who studies coral reefs in a country with one of the lowest per capita emissions rates in the world. And as someone born about 1980, I think as well all the time about the intergenerational inequity of the coral reef crisis and the global climate crisis, and the fact that the world that our children and future generations are going to inherit depend on the choices that we're willing to make right now. I believe we have to go beyond simply understanding that aggressive climate action is needed and expecting or hoping that someone else is going to do it for us, and that we instead need to start wielding the power that we collectively in this room have, using our connection to the climate crisis through our love and experience and knowledge of coral reefs and what's happening to them, and our collective expertise and privilege to advance climate solutions. We need to start having honest conversations about what real solutions are and what we're willing to do in our own lives, what we're willing to change, and what we're willing to sacrifice in order to accelerate solutions. For me, this was driven home by my son, who's in the audience today and probably dying that I'm showing a photo of him. This was 6 years ago during COVID. We were at home together. I was juggling homeschooling him while trying to work, and he had just heard me give yet another talk on Zoom about the coral crisis. And he asked me in this way that kids have, where they just don't mince words, and he said, "Mom, you talk a lot about how everything that you're doing is good for corals, but I don't understand. What really is it that you're doing that's going to save them?" And he just eviscerated me, right? Yeah, no one can do it better than our kids. And I started with my knee-jerk reaction that we all have this spiel about whatever it is we're doing is going to save coral reefs. And I just could feel it evaporating, like it just didn't hold water. And so that conversation, coupled with what happened at Christmas, really gave me pause, and it made me start rethinking everything that I do. And I'm not going to make this seem like it was overnight that everything magically came together. This has been a long, hard grind over the past 6 years. But what I want to do with my remaining few moments is share with you the path that I've been attempting to forge that is better aligned with my values, and that I hope will ultimately manage to move the needle even the tiniest bit to help ensure a better future for my son and for coral reefs. So I believe that this starts for all of us with individual climate action and thinking about our own personal emissions caps. And so there's lots of things that we can do to change our own lifestyles. And I'm primarily speaking to the people from the countries with very high emissions rates. So in my own life, I've been making changes over the past year, and I'm certainly not perfect, and there's way more that I can do, but I'm just going to share with you some of them. Transportation. I take the bus a lot. I bike very infrequently because I'm a scared biker, but I like to pretend I'm a biker. But I take the bus a lot, and I walk a lot, and I try to drive less, and I try to fly a lot less than I used to. Dietary changes. Transportation and diet are huge greenhouse gas emissions contributors, if you're just not familiar with why I'm highlighting these particular changes. But diet, I replaced red meat in my diet with lower emissions sources, and I hope I'm slowly working back to my vegetarian roots. Banking. We all bank somewhere, and at least in Canada, I can say that a lot of the major banks, basically all of the major banks, are deeply invested with fossil fuel companies. And so about 4 years ago, I moved all of my banking, my loans, my investments, et cetera, from one of the big fossil fuel banks to a local, small local credit union. And voting. For those of us who have the right to vote, we should be exercising that, and not just in federal elections, but at our state and provincial elections and municipal elections, because climate action happens at every jurisdictional level, and we need to be electing climate solutions candidates and then holding them to account. So this is really an invitation for you to just start maybe contemplating what changes you might be willing to make in your own life, and don't try to do everything at once. But if everyone committed to one change this year, and then you can kind of get used to that change, and then maybe think about another change, a second change a year from now, and keep going like that. In my research program, inspired by Ove's 2019 report on the high-level panel for a sustainable ocean economy that he talked to us about last night, which is really about quantifying how much we could harness the power of the oceans to close the emissions gap, I started a national research agenda called Blue Carbon Canada. And this came together really out of conversations with a lot of different government agencies and NGOs in my home country, asking them why Canada was not already including our oceans in our nationally determined contributions for the Paris Agreement. And the answer was a lack of science. And that's certainly not always going to be the answer, but in this case it was. And so we now work together with blue carbon scientists from across the whole country at government agencies, universities, and NGOs, and we are doing the science and providing the estimates that are needed so Canada can include our oceans, we're a country with one of the world's longest coastlines, into our NDCs. I'm also a big believer that climate solutions require interdisciplinary thinking and teams and multi-sectoral work. And so tomorrow's climate action workforce has to be trained in this regard. So together with colleagues at the University of Victoria from right across campus, people I had never met before and didn't know were on campus, but it turns out they are, and they've been amazing colleagues, we started a graduate training program called Coastal Climate Solutions Leaders. And this has become one of my favorite parts of my job because the trainees are absolutely amazing. And if you're interested, you can take a look at our website, and I would love to talk to folks about this more. It's really working, and it's all due to the strength of the trainees. And then to answer the early career scientists' question from last night about how do you go beyond preaching to the choir, take every opportunity you can to speak to whoever and whomever about climate change. So I had the opportunity to speak to this amazing journalist, Emily Aitken, a few years ago. She was commissioned to write a piece on climate change for GQ. And so I did the interview with her, and we landed on the cover of GQ, and I'm not delusional enough to think that anyone on the planet bought this magazine because it said climate change on the cover. I know everyone bought this magazine because Nick Cage is on the cover holding a big snake. But some people might have thumbed through that magazine and at the end of that experience understood a little bit more about why the difference between 1.5 and 2 degrees Celsius actually matters. And so I talk to people about climate change and climate solutions every chance that I can get, and that's at universities around the world, on podcasts, to the public, from everything from retirees groups, down to school children, to investment bankers, to petroleum geologists, anyone who wants to hear about climate change. And here's the secret I'll let you in on. They often, always, what they want to hear about is coral reefs. And then what they get is something about climate solutions, just as you might be now. So take these opportunities. In Victoria, where I live, I have also been building networks with climate solutions professionals from across networks so that we can start to do the type of community-led climate solutions work that is needed. And more, I'm using my position and my privilege as a tenured faculty to speak out about climate solutions, such as the fact that Canada should and could be harnessing its oceans to reach its climate goals, and more recently, to actually try to hold our Prime Minister to account because he seems hell-bent on building pipelines regardless of the cost to our environment or the climate. So this is just an array of the types of things that I've been doing over the past couple of years. I have lots of ambitions to do more, and I fully recognize that the things that I've been able to do are a reflection of the privilege that I hold and the position that I'm in and the opportunities that I have. But I also want to say to each of you that everyone in this room has privilege as well, or you wouldn't be here, because there's lots of people who aren't in this room. You have more privilege and power and opportunity than you know, and I hope that this talk and the examples that I've given you will at least give you a bit of food for thought so that you can start thinking about what actions you could start taking to advance climate solutions. Because you are not giving up, and neither am I. And the fact that we cannot save everything and every reef does not mean that we cannot save anything, and everything that we can save is worth saving. This planet is the only home we'll ever have. There's no place like it. And home is always, always, always worth it. Thank you. Thank you so much. Thanks. I don't have any time for questions while we're
Thank you, Julia. That was a really powerful, thought-provoking talk. So please, if you want to ask Julia any questions, she will be around. But otherwise, we haven't got time for questions now, so please go straight to your concurrent sessions. Thank you.